will talk about well, maybe not so common approaches in uncertainty quantification and uncertainty modeling based on intervals. And that's the topic of our research in our research group for several years already now. And with this topic, we try to bring uncertainty quantification tools really close to application, where maybe you are facing scarce data or you don't have enough confidence in your stochastic background or whatever probabilistic background to approach your uncertainty problem with these advanced tools. So we're trying actually to lower the threshold a bit with respect to uncertainty quantification tools. We are not only focusing on interval methods in our group, we also have different, several different research lines, but I will talk mainly about the interval methods today. Maybe just to give a general overview of who we are part of a research group, Reliable and Robust Design Research Group, part of a division that is mainly working on system dynamics. So that's also why many of our applications relate to dynamical simulations, but we are broadening towards many other domains currently as well. So we have been doing uncertainty quantification research for quite some time now, and currently the main objective of what we are doing, as I said, is to bring these simulation techniques, design techniques that introduce uncertainty into the design problem closer to industrial practice, design in industrial practice, but also manufacturing practice, because we see a lot of challenges there in manufacturing. On the one hand, you have quite fancy manufacturing simulation tools. One of the tools we are working on, for instance, is the welding simulation. They can predict quite in detail what is happening during the welding process. But of course, you are facing a lot of uncertainties there. And so we are not only focusing on the design aspects, what you can do with numerical tools in design, but also in process simulation, for instance, lately. One of the goals in this respect is, for instance, to look at UQ-enabled digital twins for process monitoring to make sure that we are assessing the process correctly, and also that we are looking at the uncertain aspects in what we are monitoring, apart from the other topics that you see on this slide. The topic I want to talk about today is about interval finite element models that's I mainly or that we mainly see in the topic of them designing under uncertainty. And it's basically an answer to several challenges that we have nowadays. We have quite fancy high resolution numerical techniques. So somebody who is facing a design problem under uncertainty usually does not want to reduce the dimensionality or the size of his model to take uncertainty into account. So somehow we have to deal with that. On the other hand, there's a lot of uncertainty nowadays that cannot be quantified by a single scalar anymore. So we have already heard the talk about random fields. So in many cases, it's spatial and heterogeneous. Also because of, in many cases, we are facing manufacturing uncertainty. And so the typical example that I usually give is the one of the additive manufacturing, where you typically have intra-variability within a component. If you look at the design or at the build of additively manufactured components, you very often have variability within the component due to thermal effects and so on during the manufacturing process. But also, for instance, the welding process that I mentioned earlier, of course, is vulnerable to this. And on top of that, you very often have lack of data. So you don't really have all the details to model this, for instance, using random fields. In that case, one possible answer could be the use of high dimensional interval fields. So let me talk about those and try not to dive too much into the technical details here, but just want to give you a general overview of what interval fields are, and what we did recently to make them applicable in the context of industrial design. And I will show you some applications. So first of all, the main idea, of course, well, of course, we start from, as I said, a non-intrusive approach. This means that we start from a nominal case, which is just a finite elements calculation as you would have it from a commercial package. That's the core of the methods, and we don't try, we try not to be intrusive. And that's, of course, the main idea when you want to make something applicable in industry, for instance. Then, of course, we all know that we can model uncertainty with a probabilistic concept. We focus here on intervals. Intervals make the quantification of the uncertainty at the input side a little bit less challenging, and you only have to know a lower bound and an upper bound. And in that respect, are often rather regarded as sensitivity studies or some large-scale sensitivity studies, rather than actually quantifying also for instance, the probability of failure. This is something, of course, they cannot do. So what you put into the model typically are intervals, and then, of course, what you get out are usually also intervals. As I said, we do this non-intrusively. How to propagate here is, of course, then one of the challenges. You can do sampling, but you can also do highly advanced adaptive response surfaces, for instance. That's something that we are focusing on recently to do the propagation. Many approaches are applicable. I do not want to focus on the propagation part in this presentation. I would rather focus on the definition of interval fields at the input side. And I started by starting off with looking at random fields. What is a random field? Of course, we are quantifying a spatial variation. For instance, this cantilever beam, we have an E modulus which is spatially varying. We consider every possible realization of that variation and try to somehow have that represented by a collection of correlated random variables over the continuous domain, and that then will make our random field or define our random field. That's a very, let's say, mature tool. So it has been used already extensively in literature, but still we see there is quite a threshold to use it in practice, especially in industrial design applications, where the objective is rather to get some kind of feeling of the levels of uncertainty that you're facing and whether or not they are relevant. Very often, we don't have the time, or we don't want to spend the efforts to have the full quantification in a stochastic sense of what is happening within the model. Of course, we have many examples where this is successful, but as I said, the main challenge is, what is then the correct representation? How do you do that? And of course, also the propagation can be quite a challenge and can take quite some time to model in practice. So the main question that we asked ourselves several years ago is, can we come up with an interval equivalent of the random field by using interval fields? And of course, we somehow want to model a dependency throughout the model. And let's take the same cantilever beam. And of course, we don't want full dependency in the model because then you have a single univariate parameter. That's not a field. But we also do not want full independency, where at each node, for instance, you would have a fully independent quantity. Because then you would end up with realistic or unrealistic realizations. So somehow some coupling has to be defined that somehow represents the spatial dependency as in a correlation of a random field. We can use them at the input side, but of course also at the output side of a problem can be very relevant to look at the actual displacement of this beam in an interval field context. And also there, of course, some realizations should not be part of the solution set. So quite some challenges to bring the concept of the intervals in the field, the world of field approaches. And that is what we try to do based on a projection that is basically inspired, you could say, by the current Leuven expansion, as we saw already earlier. So in a zero mean sense, you can write that expansion in this form, where these parameters, of course, are your stochastic variables. Well, we define an interval field basically in the same in a similar way, where we also use some spatial representation or some spatial part in our representation of our field, which is fixed. And then we multiply them with interval quantities in this case. So we started from that idea and see what we can, how we can model uncertainty if we approach it like this. As I said, we inherit the idea of the spatial shape functions in our approach, but rather than having uncorrelated random variables, we are now talking about independent interval variables that, of course, on their turn, scale the basis function. For instance, the very basic scaling of an interval on top of a base function would look like this, and then you include, of course, any possible realization which is in between the lower and the upper bounds. So that's the basic idea that we started working on now several years ago. And of course, the main question then, of course, is how will you quantify these? Because of course, in a KL expansion, you know that once you have defined your correlation structure, that you can easily come up with your eigenvectors here. But yeah, how to define these base functions in an interval field context? It's not so easy. And of course, we do not want, as I said, that to be very complex, because we want to have a method that is easily accessible, a low threshold. So we started by looking at different possibilities, and we came upon the idea of introducing what is called interval or inverse distance weighted interpolation. What does that mean? Well, if you would define intervals at several locations, take this as your FE model, and you would define intervals at several locations, an inverse distance weighting function actually takes the distance in every point towards these reference points and uses that inversely to calculate a weight function of that specific interval. Actually, you are weighting the intervals based on the distance. If you would take the uncertainty level in one point, you are using the distances to all reference points to calculate their specific weights to the uncertainty in that point. That's what we called inverse distance weighting. It works quite well and has a nice advantage that you can, for instance, build interval fields as soon as you have some IDs on uncertainty levels, interval levels at several locations. So that's the basic idea of the inverse distance weighting. And after which, of course, the propagation part is still to be performed. And this, of course, then can be done by considering the interval problem as some hypercubic, because all these intervals are independent, and hypercubic interval problem that has to be solved. I will skip this because, as I said, I will not talk too much about propagation here, but just show you how we faced some of the large challenges that we had over the past years when we tried to apply this in practice. So as I said, we try to make the method work for industrially sized models, and then we very often face very high dimensional models where you are having a finite element model with several millions of degrees of freedom. And you do not want to change that. If you want to do a quick assessment of your uncertainty levels, you want to make use of that model. And then, of course, one of the challenges is that in the inverse distance weighting basis function, you have to calculate your distance measure at every possible location in your domain with respect to each reference value. And that's, of course, when you have millions of degrees of freedom, that becomes quite expensive, and it basically makes the method impossible to apply. So we defined, what we did is we used an alternative grid to define our interval fields, and even made it, we optimized this by using sparse grids that can adaptively refined if necessary. What do I mean by that? It's quite clear that if you look at this inverse distance weighting approach, this p-value here somehow determines the gradients, the possible gradients of your fields over your domain. And that on its turn then defines the required level of accuracy or refinements in the grid that you use. And we use that as a basic idea to use sparse grids to define, for instance, interval fields on top of a quite dense finite element model, as you can see here. I will spare you the mathematical details, but it basically comes down to the fact that we are introducing sparse grids, and we find the sparse grids in those locations where we need them. And then we can reduce the amounts of distance calculations that we have in our basis function definition. Just to show you an example what that means, for instance, in this still rather small model, I have to say, because it's not yet of the size of what we had in mind here, of course, so with about 26,000 elements here. But we used it as an example to study. We defined some uncertainty levels at several locations in this domain, and then considered interval fields based on the order of the p order that we have here. And for instance, our method showed out to be quite successful. If you have limited gradients, of course, the effect of your sparse grid interpolation is less as if you have high gradients. But as you can see here, by using this adaptive sparse grid approach, for a value of p equals 9, we could reduce the number of interpolation points for our basis function with a factor of 10, which is already quite substantial. We applied this method on the toy problems, on this toy problem, but I've also worked on the methods in more detailed models, and even collaborated with industry on I cannot tell you with whom, but this is actually a part that we studied with over 1.5 million degrees of freedom using the interval field approach to quickly assess the uncertainty levels that they were facing in the casting process of this component. Okay, let's keep an eye on the timing. What we also developed is the concept of the local explicit interval field, and this is basically an answer to the fact that very often you want to assess, or we got a question from industry: can you assess the uncertainty level very locally in our problem? So, for instance, we have a location where we are. Our design is quite sensitive in manufacturing to uncertainty, to variability in the manufacturing process, but it's only locally at that point. This is something we cannot do with classic inverse distance weighting, because these base functions have the tendency to be present all over the domain, because they are distance are defined by the distance. So we came up with what we call the local explicit interval fields, which again, I will not talk too much about the details here, but you can understand the basic idea by looking at the basis functions here that of course are forced to be zero outside of a given local domain that you then define, some sort of radial basis function that you use in this sense that is forced to zero at some locations. And that, of course, gives then a huge difference. This is, for instance, the very same model, a 1D model, where you have 3 intervals at several locations. This is what happens when you use inverse distance weighting. This is what happens when you use these local explicit interval fields. And of course, you can see quite clearly that those become quite independent uncertainty levels at several locations, while in this case, all these realizations show that they are still coupled. And of course, an additional advantage here, again, is that we need much less distance measures because, of course, we force the base functions to zero at large parts in our domain. To show you what we can do with this, again, the same component that I showed you earlier, where we then introduced some intervals, for instance, on E moduli that we introduced at several locations. And then for instance, if you, as I said, if you are facing a problem with respect to, for instance, in this case, the manufacturing of the component, and you have observed locations where the problem is, or where your component is quite sensitive, you can introduce your uncertainty very locally at those locations, and then come up with an assessment of the uncertainty levels on, for instance, stresses in your components. Okay, one last recent development that I would like to share with you is what about auto-correlation or cross-correlation then between intervals, because that's quite a topic in literature, and how to deal with that, because we don't really have in classic interval analysis a tool to deal with correlation between intervals, and then you have to go to convex approaches or convex analysis. We also study this in the context of interval fields, and basically if you are looking at intervals and you want to couple them, one of the ways to do this is to use the concepts of admissible sets. And then this basically comes down to defining copula functions, bivariate copula functions between any combination of two parameters, and then nest them into some sort of multidimensional representation of your copula, what we call admissible sets. Just to give you the general idea of what we do here in the context of interval fields, you can imagine that if you do this, you cannot apply this, of course, on each and every location in your model. That would not work. That would make it infeasible. But you could use these independent alpha i's that I introduced earlier. So the intervals at independent locations in the model, to build these admissible sets and to somehow link what is happening in between those. So this takes the method that I introduced earlier, where we introduced independent intervals at every location. This takes this actually to the next level, where now we don't have to necessarily have independent intervals at these locations. You can introduce dependency. So I don't really need this slide. The basic idea here is that if you would have several locations, that you can link those 2 by 2 in such an admissible set, but you could also work with cross correlations. So if you have two interval fields that somehow should be linked to one another or should be related, you can of course use this method as well to define some dependencies between cross correlations between the two fields that I show here. I will skip those slides just to be able to tell you a bit about the recent applications, and just to keep my presentation also in time. Well, one of the applications I wanted to share here that we did recently is in crash analysis. So as I said, we try to focus on, or we try to work on complex problems and on large finite element models. And of course, the crash analysis is something that is quite complex and very sensitive to many uncertainty levels, or to many uncertainties. And so we focused here in this study on the crash box performance that is typically in an automotive structure, and which is often simulated. And then people are looking, for instance, at the peak level of the forces during a crash analysis, or at the mean level of the force during the crash. And this is state of the art. So this is what they do in simulation nowadays in automotive. And of course, if you look at this simulation, you can already imagine that it's quite sensitive to a lot of uncertainties that are in here. And one of the main uncertainties is actually the boundary condition. So they're crashing this box into a rigid wall, while in practice, very often this is of course not rigid. This is in an accident, you have of course a compliant structure that you crash against. So what is the performance then, and how should you take that compliance into account? This is one of the things that we tackled using interval fields. So you could say, okay, you define some sort of stiffness with respect to the environment using some springs, and then you can do this in a scalar way, and you get some intervals on, for instance, the peak forces and the mean forces. Then you don't have really have a field approach. You don't really need a field approach. You could say, but you could argue in this case, if you would introduce a compliance between the structure and the environment, you could say that it's not really defined in first place how that compliance is distributed. And so there could be uncertainty, spatial uncertainty. So what we did is we defined interval fields to define the stiffness with respect to the environment here. And of course, then you get all different crash modes, as you can see here, that of course will result in quite different peak forces. And this enables, of course, the analysis to be much more representative for actual crashes, because of course this will happen. These are cases that are of course likely to happen. And what we found out is that the amount of uncertainty that you get when you introduce this in an interval field kind of approach is substantially larger than when you do not do this. And that is of course because you get many different buckling modes, especially because of the fact that your stiffness is not evenly distributed with respect to the environment. So quite interesting study here that can tell you, of course, you do not know the actual uncertainty levels very often, but at least you can assess somehow the uncertainty level that you have, or the sensitivity of the approach that you're using with respect to the spatial uncertainty levels that are in your structure. Yeah, this is the same analysis, but with 8 control points. I will skip that as well. The final application that I wanted to share here is basically the question we ask ourselves here is now, okay, we have these interval fields, and how do these compare now to random fields? And to what extent can you find an analogy? We already discussed the analogy in the definition phase of the interval fields with respect to the random fields. But if you propagate to the results, can you choose between them, and what about the results? How do they differ? And this is something we studied in this publication based on this model, where we introduced random fields, very simple random fields, and isotropic Gaussian random field, and also an interval field to represent the same uncertainty, namely an E modulus in the solar wind array that we have here. And what did we do next? Well, we tuned our interval fields using an approach that I did not really discuss here, but such that the gradients that we have in our interval fields somehow are similar to what we get in our Gaussian realizations of the random field. So that's the analogy that we try to implement. And also we force the global bounds to be at ±3 sigma, again, of the full realization set. And quite interestingly, if you look at the results now, so this is at the input side. So you see the blue dots here are the Monte Carlo samples that are generated on the input side of the problem. The red holes are the holes that we get when we use the interval field approach. And you can already imagine that if you look at this at the input side, they are quite similar. So if you look at the output side, for instance, in this case, the velocity levels that we have in the landing phase, the upper bound and the lower bound actually, well, are not that much different. And you could even say, well, if you want to do the uncertainty assessments on what is happening in your model, they score quite equal. This this work has been published, so you can look for the details in that reference. So to conclude, I discussed the interval fields using mainly inverse distance weighting. We are working on quite some methods to have them applicable in industrial sized problems. I discussed sparse grids, local basis functions, and multivariate analysis. And we believe that we can or that interval fields can really be an alternative, not really a competitor, but let's say complementary to random fields when you have scarce data, or your objective is mainly to have an assessment of the sensitivity of your analysis towards spatial uncertainty levels. And with that, I'd like to conclude my presentation.